All right, the end of chapter 6 in your textbook talks about electron configurations, which you might be familiar with already. The beginning tries to give a little bit more background on what the behavior of an electron is, and it starts out by talking about light and electromagnetic radiation, and so it's a little bit complex and interesting, and looks a little bit like physics here. The first thing we'll talk about is just mention, since electromagnetic radiation, visible light, UV radiation, microwaves behave as waves, we are just getting some terminology here that has to do with waves. So the distance between two crests of a wave would be the wavelength. That would be measured in meters. It is, a unit of length. And then how many times you see a wave go up and down per second would be the frequency. Instead of F for frequency, we have this Greek letter nu that looks a little bit like a V, but this is the frequency, and that is measured in per second. So how many per second? Here we have this in meters, and here we have this in 1/second, which we can also express as seconds to the -1, which we can also express as hertz. So hertz, which is Hz, is a unit that means seconds to the -1, or per second. If you multiply these two terms together, the meters per cycle, or the meters per wave, and you multiply that by the frequency, which is the cycles per second, you get the speed of the wave, how many meters per second the wave is traveling. And for light waves, that ends up being the speed of light. If these were visible light waves, these would all be different colors because they have different wavelengths and different frequencies. So all these three waves that you see here would be seen as different colors of visible light. If they were sound waves, they would be heard as different notes, different pitches of sound. These two waves would be the same color of light or the same pitch of sound. The thing that's different about these two waves, they have the same wavelength and the same frequency, it's just that one is going higher than the other. So it would be the same color light, only brighter, and it would be the same note of sound, only louder. And this height is the amplitude. The height from the middle of the wave to the top is the amplitude. So we're going to be dealing with light, either visible light or other types of electromagnetic radiation, and these all travel at the speed of light. So we mentioned that the wavelength times the frequency would be the speed of that wave, and for us we're going to be dealing with the speed of light, which is 2.998 times 10 to the 8th meters per second. So let's use this information to get the wavelength from a frequency and the frequency from a wavelength. Here we have our equation that the speed of light is the wavelength times the frequency, and we have the value for that. If we solve for the wavelength, which is lambda, we get the speed of light c over the frequency. Before I put the frequency down here, I'm going to get it into hertz instead of megahertz. So here we have 103.3 megahertz. I put this in scientific notation in case it makes it easier for some people to see. That's 1.033 times 10 to the 2 megahertz. And then a megahertz is 10 to the 6 hertz, which makes 1.033 times 10 to the 8th hertz. Or if we want to write the hertz as seconds to the -1, that might make the units easier to cancel. So we'll go ahead and cancel the seconds. While I'm at it, I'm going to go ahead and cancel the 10 to the 8th. And this makes a wavelength of 2.909 meters. Here we're trying to find the frequency instead, which would be the speed of light over the wavelength. I'll go ahead and get the wavelength in meters. A nanometer is 10 to the -9 meters, and 515 nanometers would be 5.15 times 10 to the 2 nanometers, so that it makes it easier to multiply by 10 to the -9. That would be 5.15 times 10 to the -7 nanometers. That is 5.15 times 10 to the negative 7 meters. I'll put that down here. And that comes out to be 5.82 times 10 to the 14 seconds to the negative 1, because the meters cancel. And so you can put this as hertz or convert it to terahertz if you want to. So you should review the diagram of the electromagnetic spectrum just to remind yourselves where visible light fits in on that spectrum compared to more energetic light with shorter wavelengths and higher frequencies like UV light, X-rays, and gamma radiation. Also some lower energy radiation like infrared, microwave, radio waves. And the visible light spectrum has wavelengths of between 380 and 740 nanometers and between 789 and 405 terahertz for the frequencies. So there's a little bit of a historical context in your textbook, and I'll try to find some cool videos that I've seen about the ultraviolet catastrophe. It sounds way more dramatic than it is. It's not like, oh, this is why all the dinosaurs died, they didn't have sunscreen. It's just that the calculations that physicists were doing on the energy being emitted by hot particles did not match the calculation. Their calculation said that cooler particles should be emitting infinite amounts of energy, which is obviously not true. And so what made these calculations work was the assumption that energy had to be certain specific values. It could not just be any number. It had to be certain values. And he wasn't sure why that was, but when he made that assumption, the calculations just worked out so much better. And then Einstein recognized that the energy that light has is not dependent on its amplitude. Like we were saying before, light could be brighter, the same color, but brighter if you increase its amplitude. This ends up not increasing the energy of the light at all. It increases the amount of light, but it doesn't increase the energy of any specific particle or photon of light. What does increase the energy is increasing the frequency. So you can probably picture this as a nice calm wave on the ocean, and then if the wind starts picking up and the ocean starts getting more energetic, the waves will look more like this. They'll have higher frequencies and shorter wavelengths. And that's what happens. You have this kind of radiation with much more energy than this radiation. The formula for how much energy a photon of light would have is equal to that frequency. Remember, we said it's proportional to the frequency, and it's times a constant called Planck's constant. So let's copy down these equations here and use them to solve some problems figuring out the energy of photons of different electromagnetic radiation. So the energy of one photon of radiation with this frequency would be Planck's constant times the frequency. I'm going to go ahead and get the frequency in hertz instead of gigahertz. Since a gigahertz is 10 to the 9 hertz, this would be 1.228 times 10 to the 9 hertz. And to make it easier for the units to cancel, I'll write this as seconds to the -1, because the seconds times the seconds to the -1 will give seconds to the 0, which is the number 1 that cancels it out. And we get 8.137 times 10 to the -25 joules. So this is a pretty small amount of energy, but it is just one photon. So that's pretty appropriate. All right, we have the same formula here, Planck's constant times the frequency. This time we don't actually have the frequency, we have the wavelength. So to get the frequency like we did before from the wavelength, it's the speed of light over the wavelength. This wavelength is in nanometers. To convert it to meters, I converted it to 7.20. That makes the assumption that we have 3 significant digits. Let's go ahead and keep that assumption. 7.20 times 10 to the 2 nanometers and 10 to the -9 meters per nanometer. So that gives us 7.20 times 10 to the -7 meters. And our frequency is 4.16 times 10 to the 14 hertz, or seconds to the -1. When we put this frequency into our equation for energy, we get 2.76 times 10 to the -19 joules. So a little bit more energy than this one, but still pretty small. All right, so how do we know the energy of a photon of light is proportional to its frequency? And that work is what actually Einstein won his Nobel Prize for. He did not win it for the theory of relativity. He worked with the photoelectric effect. And so that is the phenomenon that when light is shined on a metal, if it is of sufficient energy, it will cause an electron to be ejected. And if it's not sufficient, then no electrons will be ejected. And so certain wavelengths of light would not eject a photon no matter how intense you made that color light. You needed a different color with a different frequency in order to make this work. So the energy of the incoming photon has to be sufficient. We were just doing some calculations on the energy of a photon. If that is enough to meet this threshold of energy, which is different for each metal, then whatever energy is left over will go into the kinetic energy of the electron. So the energy coming in, some of it goes to the metal and some of it goes to the electron. The energy that is going into the electron, the kinetic energy, is the difference between the energy that's coming in minus, if you think about it, this threshold energy as a toll that you have to pay. So you have some energy coming in, you have to pay a certain toll that the metal is going to just absorb. That's the threshold energy, and whatever is left over, that can go into your electron as kinetic energy. And so the more energy you give the electron, the faster it's going to go. It's kinetic energy, the energy of motion. And if the incoming energy is not enough to pay that toll, then you are not going to be able to have the electron ejected at all. Once you know how much kinetic energy an electron has, you can calculate how fast it's going. This v over here is an actual v, not a nu. So this is the speed. I'm using v for velocity. So that is the speed, not the frequency. So this is the speed or the velocity, not the frequency. So you can calculate the speed of the electron as well. So one more comment about this formula over here. If instead of using joules, you replace joules with an equivalent unit. So joules, if you reduce it to SI units, so if everything's in kilograms and meters and seconds, then a joule is a kilogram meter squared per second squared. So if the energy that you have, instead of giving it in joules, you have it in kilograms meter squared per second squared, then you have your kilograms here. This is the mass. Here's the mass of an electron right here. Then this square of the speed would be meter squared per second squared. So that will help you figure out the speed of an electron as well. Another unit that is equivalent to a joule is an electron volt. Historically, these threshold energies have been measured in electron volts rather than joules, and so you can convert it using this equivalent relationship here. So let's scroll up a little bit and do this problem. I think the first thing that we can do is convert this threshold energy into joules. Then we can get the energy of the photon in joules and compare them. So this is a straight conversion, the 2.3 electron volts. We use the relationship as a conversion factor, and we come out with 3.7 times 10 to the negative 19 joules. Now we need the energy of the photon of light, which is Planck's constant times the frequency. And let's put Planck's constant here as well. So in this problem, we're not given the frequency, we're given the wavelength. So up in this corner here, I reviewed this speed of light being the wavelength times the frequency. And so the frequency is equal to the speed of light over the wavelength. We can go ahead and replace that for the frequency in this equation. So this frequency is the speed of light over the wavelength. So we can replace that here. So our energy is Planck's constant times the speed of light over the wavelength. So let's go ahead and put those in here. Planck's constant is 6.626 times 10 to the negative 34 joule seconds. The speed of light is 2.998 times 10 to the 8th meters per second. And the wavelength is 675 nanometers. A nanometer is 10 to the negative 9 meters. So I'm just going to replace nanometers with 10 to the negative 9 meters. When we multiply all this, the meters cancel, the seconds cancel with the inverse seconds, and so we end up with joules, and we end up with 2.94 times 10 to the negative 19 joules. This is smaller than this, so 2.94 times 10 to the minus 19 joules is less than the threshold. It does not meet the toll. It cannot pay the admission price. And so there is not going to be electrons ejected. So will electrons be ejected? The answer is no here. All right, let's try another example of this. We're still working with potassium, and we've already figured out that this is equivalent to 3.7 times 10 to the negative 19 joules from the previous problem. So now we're going to find out the energy of a photon with 375 nanometer wavelength. So similar to before, we're going to use this energy equation, Planck's constant times the frequency. The frequency is the speed of light over the wavelength. So this equation becomes this formula here. Again, that's because the frequency is the speed of light over the wavelength. So we can replace that with that. So here I put in Planck's constant, 6.626 times 10 to the negative 34 joule seconds. The speed of light, 2.998 times 10 to the 8th meters per second, or meters times inverse seconds. And then nanometers, again, I replaced the nano with 10 to the negative 9. So 375 nanometers is 375 times 10 to the negative 9 meters. So this comes out to be 5.30 times 10 to the negative 19 joules. This is larger than the threshold now, so we do have enough energy to eject an electron. So here we have the energy of the photon, here we have the threshold. The kinetic energy of the electron is the energy left over when we take the incoming energy of the photon and we subtract that threshold. Again, it's like a toll or a tax. So these are both 10 to the negative 19 joules. So we can actually line these up, and it becomes 1.6 times 10 to the negative 19 joules as the difference here. And I'm going down to 2 significant digits just because of the place values in the subtraction. So that is the kinetic energy of the electron. So now that we've figured out the kinetic energy of the electron, we want to also try to figure out its speed, its velocity. So let's go ahead and solve this equation for the velocity. 2 times the kinetic energy of the electron would be the mass times the velocity squared. We divide both sides by the mass of the electron, and we get 2 times the kinetic energy of the electron over the mass of the electron is the velocity squared. So that means we have to take the square root of both sides, and we get that the velocity of the electron is 2 times the kinetic energy of the electron over the mass of the electron, the entire thing underneath a square root. So let's go ahead and do this over here. And again, instead of joules, we're going to replace this with kilograms meter squared per second squared. That's just going to make it easier. So we're going to have 2 times 1.6 times 10 to the negative 19 kilograms meter squared per second squared. And here we're going to have the mass of the electron, which we saw on the previous page. It's 9.11 times 10 to the minus 31 kilograms. The kilograms are going to cancel. This becomes 3.5 times 10 to the 11 meters squared per second squared. And when we take the square root of that, it becomes 5.9 times 10 to the 5th meters per second. So this is the speed of the electron, This is the energy of the electron, the 1.6 times 10 to the negative 19 joules, and the answer, yes, an electron will be ejected with this energy and this speed. All right, one other thing that was noticed about elements, if you have the atoms spread really far apart, like in a gas that's under vacuum, and you have the atoms of an element split really far apart, and you excite those atoms with some energy, with heat or electricity, you can find line spectra. So that's different from when you have something that is molten, glowing, melted iron, and you look at the spectrum from that. It is a fairly continuous spectrum, but if you had iron as a low pressure gas, or more commonly you have something that's a gas as a low pressure gas, you can just get the line spectra. So there are just certain wavelengths that are emitted by these low pressure gases. Hydrogen is the simplest element, it only has one proton and one electron, and so there are just a very few lines in that line spectrum, and the wavelengths were measured, and this equation was discovered to tell what these different wavelengths are, with n being the energy level of the electron that is on the element. So for hydrogen, the simplest element, here I have I'll put the nucleus over here. This is the nucleus. So we have the nucleus in the middle, and the electrons are circling this nucleus at different energy levels. So we have the very closest level as n equals 1, then n equals 2, n equals 3, and so on. So that's what these n's are in the equation. And it was discovered that 1 over the wavelength that's being emitted had these certain values. The Rydberg constant times 1 over the square of one level minus 1 over the square of another level, that this relationship worked for the different lines that you find in hydrogen's line spectrum. Since the wavelength has to be a positive number, not a negative number, the value of n1 has to be smaller than the value of n2, because if not, this will be a negative number and the wavelength will be a negative number. So for this equation, n1 is always less than n2. If the wavelength of light is being absorbed by the electron, it's going to jump to a higher level. If it's being emitted, then it's going to fall to a lower level. So whether it's being absorbed or emitted, we're not going to worry about the sign of the wavelength, because the wavelength is always going to be positive. I just wanted to show you figure 6.13 in your textbook. It has a picture of a continuous spectrum, so all of the different colors are being represented, versus some line spectra. This one even is hydrogen. So it's fairly simple, just a few lines in the visible range. We have one at 656.3 nanometers. So an angstrom is 10 to the negative 10 meters. It's 1/10 the size of a nanometer. So this would be 6,000 angstrom would be 600 nanometers. 7,000 angstrom would be 700 nanometers. So we have this line over here at 656.3 nanometers, and this line over here at 486.2 nanometers. Those are two of the very famous lines for hydrogen. In addition to the visible line spectrum of hydrogen, hydrogen also can emit wavelengths in the UV range and in the infrared range. These particular examples end up with wavelengths in the visible range, and these are called the Balmer series. So just for a little trivia here, in addition to the visible lines when N1 is 2, we also have some UV lines called the Lyman series when N1 is equal to 1, and some infrared IR radiation being emitted called the Paschen series when N1 is 3. In addition to this equation, we have a Bohr model equation that we are going to be using in the next section, where instead of focusing on the wavelength, we focus on the energy of the different electrons and how the energy is being emitted or absorbed. But for now, let's go ahead and solve these two for the wavelength with these distance between level 2 and level 3 and the distance between level 2 and level 4 corresponding to certain wavelengths for hydrogen. Alright, so the level 2 to level 3 difference is represented by this 1 over 2 squared minus 1 over 3 squared. So if you solve that, you get 0.1389. Then when we multiply this by Rydberg's constant, we get 1.524 times 10 to the 6 inverse meters. That's 1 over lambda, so we have to take the inverse of this to get lambda. So that would be 1 over the 1.524 times 10 to the 6 inverse meters. And this becomes 6.563 times 10 to the minus 7 meters. A lot of times visible light is expressed as nanometers. You saw that in our spectroscopy lab. So let's go ahead and convert this to nanometers. And when we do that, we get 6.563 times 10 to the 2, or 656.3 nanometers. And this is one of the bands that we see in hydrogen's line spectrum. So what about the difference between level 2 and level 4? So that would fit into the equation this way. And when you calculate that, it is 0.1875. And then when you multiply that by Rydberg's constant, you get 1 over lambda being 2.057 times 10 to the 6 inverse meters. When you take the inverse of that, it is 4.862 times 10 to the minus 7 meters. And then if you convert it in the same way we did above, it ends up being 486.2 nanometers. So this is the other visible, one of the other visible lines in the line spectrum of hydrogen. All right, I think I will wait till the next video to relate this to the Bohr model, the energy formula that we're going to be looking at as well.